What if the oldest thing in the universe is not a star, not a galaxy, and not even the first light from the first suns? Far beyond the Milky Way, beyond the earliest galaxies James Webb can see, there is something older still, a faint ancient glow that has been travelling across space for almost the entire history of the cosmos. Today, the journey begins at the edge of visible time itself. If this kind of deep space mystery is fascinating, please like the video and subscribe to the channel. The universe first appears as space. It appears as darkness carrying points of light, with no visible mark showing that the darkness also contains time. Yet this is the first and quietest truth of the sky. To look outward is not only to look across distance, it is also to look backward into earlier states of the universe. The night does not present itself this way to ordinary sight. It seems immediate. A star seems present where it shines. A galaxy seems to exist where it glows. The eye receives light and gives the feeling of now. Astronomy gradually corrects that feeling. Light does not arrive instantly, it travels. It needs time to cross the intervals between one place and another. Because of that delay, everything seen in the sky appears not as it is in the present moment on Earth, but as it was when its light first began its journey. The universe therefore acts like a vast archive written in light. Near things are recorded from the recent past. Far things are recorded from deeper time. The greater the distance, the older the visible message. This relation between distance and time shapes all cosmic seeing. On Earth, distance usually means separation in space alone. A mountain beyond a valley is seen almost at once. A cloud on the horizon is seen almost at once. Even the moon, though far above Earth, is seen with a delay so small that daily life does not notice it. In the universe beyond the solar system, delay becomes meaningful. Light from the sun takes a little more than 8 minutes to reach Earth. Light from Neptune takes several hours. Light from the nearest star beyond the sun takes more than 4 years. Light from the bright stars scattered across the Milky Way often takes tens, hundreds, or thousands of years. Light from distant galaxies takes millions or billions of years. At the largest visible scales, the sky stops behaving like a picture of the present and becomes a layered record of earlier ages. The eye still sees light, but the mind must learn that each beam arrives carrying a different age. That's why the oldest thing visible in the universe is not approached first by naming an object. It is approached first by understanding how seeing works at cosmic scale. The universe does not reveal all eras at equal depth. It reveals them according to the travel time of light. A nearby star shows a recent chapter. A remote galaxy shows a much older chapter. The sky is not one single moment spread across space. It is many different moments arriving together. The stars overhead seem to belong to one night, yet each one delivers light released at a different time. This means that the visible universe is not only large, it is mixed in age. The darkness between points of light does not separate one present object from another present object. It separates many different pasts. This can feel unnatural at first, because ordinary experience trains the mind to join sight with immediacy. A hand is seen where it is, a tree is seen where it stands. Even a distant hill belongs to the same shared moment of the landscape. In cosmic observation, that instinct no longer holds. Light moves at a finite speed. Finite means limited, not instant. It is very fast, but not infinitely fast. That simple fact changes the meaning of the sky. Every visible thing beyond Earth is observed through delay. The universe becomes legible only because light takes time. If light crossed space without delay, the sky would show a more nearly simultaneous cosmos. Because light must travel, it brings history with it. The darkness of space is therefore not empty of meaning. It is the medium across which the past remains visible. At this outermost level, the universe can be imagined as a set of receding shells of time. The nearest shell contains the most recent visible events. Beyond that lies an older shell. Beyond that, older still. This image is not perfect, because the universe is not centered on Earth in any deep physical sense, and different objects move and evolve in their own ways. Still, as a guide to seeing, it is useful. Looking farther means looking earlier. Telescopes do not merely magnify. They also deepen the reach into time by gathering light that has travelled longer distances. A more powerful telescope does not create the past. It receives fainter and older signals that smaller instruments cannot collect clearly. This is why astronomy often speaks of deep fields and deep surveys. Depth in the sky is also depth in time. There is another quiet consequence of this. The universe has a history that can be read not only from matter but from light itself. Light preserves evidence of where it comes from. Its colour, intensity, pattern, and spread contain clues to temperature, motion, composition, and age. When astronomers study distant objects, they do not touch them. They do not travel to them. They read the arriving light. The sky becomes a record because light is both messenger and memory. It carries the mark of the conditions under which it was released. For stars, that light tells of surface heat and chemical traces. For galaxies, it tells of structure, motion, and change across time. For the universe as a whole, it can reveal conditions from extremely early eras. The question of the oldest thing that can be seen is therefore really a question about how far back light can still speak. This also means that visible age is not the same as actual age. A nearby old star may itself be extremely ancient, almost as old as the Milky Way. Yet the light reaching Earth from that star may have travelled for only a few thousand years or less. A far galaxy may be younger in its own stage of development, yet its light may have been travelling for more than 13 billion years. One kind of age belongs to the object, another belongs to the journey of its light. The sky contains both meanings at once. Some objects are old in themselves, some signals are old in transit. The deepest visible past is found not by asking only which object forms earliest, but by asking which light began its journey closest to the beginning of the visible universe. From the widest perspective, this is the framework within which the whole search must proceed. The visible universe is not an even spread of present things. It is a time archive built from delayed light. Every observation becomes an act of recovery. A telescope points outward, but in another sense it points backward. It gathers light that has crossed the dark for years, for ages, for spans so large that human history becomes small by comparison. The oldest thing that can be seen must therefore lie at the far limit of visible look-back time, at the boundary where light first becomes able to travel freely across space and remain detectable long after its release. That boundary is not yet named here. It is enough, at this widest outer level, to understand that the universe can be seen as history because light is not instantaneous, and the sky becomes ancient because distance turns into memory. So the night above Earth is more than a ceiling of stars. It is a layered record of cosmic time. Near lights speak from the recent past. Far lights speak from deeper ages. The universe presents itself in delayed fragments, all arriving together, each one carrying its own timestamp written not in words but in travel time. Before any ancient star is singled out, before any early galaxy is examined, before the deepest visible glow is recognized, the first truth remains this broad and steady one. The universe is something seen through time. Its vastness is a form of memory. Its darkness is crossed by signals from many eras at once. And the search for the oldest visible thing begins not with an object, but with the simple, transforming fact that to see far is to see long ago. Among the visible things nearest to Earth, some of the oldest are not distant galaxies, but stars within the wider reach of the Milky Way itself. They do not look ancient in any dramatic way. They shine with the same quiet steadiness as many other stars. Their great age is hidden inside their chemistry, their mass, and the long persistence of their light. These stars belong mainly to the halo and other old populations around the galaxy, where some stellar bodies preserve conditions from the early history of cosmic star formation. They are often called ancient in a relative sense, not because they exist from the first moments of the universe, but because they form very early compared with most stars now visible in the sky. They are survivors from a young universe that has already cooled and already begun making stars out of simple gas. In them, age is not seen as damage, it is seen as endurance. A star becomes old not by looking worn, but by continuing to exist through enormous spans of time. The stars that last the longest are usually those with lower mass. They burn their fuel slowly and remain stable for billions of years. Massive stars live quickly and die quickly. This is one reason ancient stars can still be seen today. If the early universe formed stars of the right masses, many of them can survive to the present era. Their existence allows astronomy to study a kind of local deep time. Instead of observing a remote object whose light has travelled for billions of years, astronomers can also observe a nearby star that has itself lived for nearly the full age of the universe. That is a different kind of antiquity. The light may be recent in transit, but the object producing it has endured since very early cosmic history. Many of these old stars are found in the galactic halo, the broad sparse region surrounding the bright disk of the Milky Way. The halo contains stars that move on elongated paths, often tilted well away from the flat plane where many younger stars gather. This gives the halo a quieter and more ancient character. It is less crowded, less rich in gas, and less active in new star formation than the disk. In that calmer environment, some stars preserve traces of conditions that exist when the galaxy is still assembling. Their orbits suggest long and complex histories. Some may form within the early Milky Way itself. Others may come from smaller systems later absorbed into it. Either way, many halo stars belong to a very old population. The most important clue to their antiquity lies in chemical composition. In astronomy, elements heavier than hydrogen and helium are often grouped together under the simple term metals. This does not mean only iron or familiar earthly metals. It means all heavier elements made later inside stars and spread outward by stellar death. The earlier stars form from gas that contains very little of this enriched material, because not many previous stars have yet lived and died. So when astronomers find a star with extremely low heavy element content, they recognize a sign of early origin. The star forms from gas that has not been much altered by earlier generations. Such stars are called metal poor. That phrase sounds technical, but its meaning is simple. It points to a star born before the universe has been strongly enriched by repeated cycles of stellar life and death. This does not mean these ancient visible stars are the first stars ever formed. Observations indicate that the very first stars are likely massive and short-lived, made almost entirely from hydrogen and helium. Those earlier stars probably do not survive to the present. What remain visible now are later survivors from the early eras that follow, stars formed from gas only lightly enriched by what comes before. They are ancient descendants of the first period of stellar birth, not direct messengers from the absolute beginning. Their value lies in how close they carry visible astronomy to that beginning, while still remaining within the local universe. They are among the oldest luminous objects that can be directly studied in detail. One well-known example is the star often called the Methuselah star, a nearby metal-poor subgiant whose estimated age approaches the age of the universe itself within measurement uncertainty. That uncertainty matters. Age estimates for stars depend on distance, brightness, composition, and models of stellar evolution, and those ingredients carry limits. Observations indicate that some stars appear extraordinarily old, but it remains uncertain exactly how close any single one comes to the true cosmic beginning. The important point is not a perfect ranking between individual stars. It is the broader fact that the Milky Way contains visible stars whose lives begin very early, within the first chapter of sustained star formation. These stars are unsettling in a quiet way. A nearby star may seem like part of the ordinary local sky, yet it may already be older than the Sun by billions of years. It may have formed before Earth exists, before the solar system takes shape, before the Milky Way settles into much of its present appearance. Its light enters a telescope today from a distance that seems modest by cosmic standards, but the star itself belongs to a remote age of formation. This difference between travel age and object age matters greatly here. An ancient halo star can be one of the oldest things visible as an object, even though its light does not come from the deepest visible past in transit. Its antiquity lies in its long survival. So the old stars near the Milky Way stand as local fossils of cosmic history. They are visible, measurable, and close enough for detailed study. Their low heavy element content, great age, and long-lived stability make them some of the oldest objects the eye can reach with telescopes in the nearby universe. Yet they do not belong to the beginning itself. They arise after the universe has already changed enough to permit star formation. They are ancient lamps lit within an already maturing cosmos. They show how early visible objects can still remain among us, shining quietly in the halo, carrying within their chemistry the memory of a young universe that is already far older than anything on Earth. Some of the oldest visible stars do not shine with strong youth or great brilliance. They appear faint, dense, and quiet. They belong to a late stage of stellar life known as the white dwarf stage, when an ordinary star has already exhausted the central fuel that once supports its earlier brightness and has shed its outer layers, leaving behind a hot, compact core. A white dwarf is not dead in the absolute sense, because it still radiates stored heat. Yet it no longer generates energy in its center by ongoing fusion. It shines by cooling. That slow release of heat makes it one of the calmest clocks in the sky. The oldest white dwarfs visible today have been cooling for immense spans of time, and because their cooling follows predictable patterns, they help reveal how long certain stellar populations have been in existence. This makes them different from the ancient halo stars considered before. Those old stars preserve age mainly through long survival and sparse chemistry. White dwarfs preserve age through a later form of persistence. They are remnants. Their present state tells not only that a star has lived, but also that it has already passed through much of its life and settled into a lingering afterglow. To find a very old white dwarf is to find a stellar body that has been cooling for billions of years after the main active portion of its life is already complete. The faintness of such an object is therefore meaningful. It is not merely dim by chance. It is dim because time has drawn warmth out of it steadily and slowly across cosmic history. A white dwarf forms from stars of modest mass, the kind that do not explode as supernovae. Over long periods they fuse hydrogen, then later expand and change form as their internal balance shifts. In the end, the outer layers drift away, and the core remains. That core is extraordinarily dense. Matter inside it is packed into a state supported not by ordinary gas pressure, but by quantum rules that arise when particles are compressed so tightly that they resist being squeezed further into the same condition. The result is a body roughly Earth-sized in diameter, but containing a mass comparable to that of the Sun. It begins very hot, but because it has no large internal furnace left, it gradually cools. This cooling is slow enough that the oldest white dwarfs can still be seen today, even though their brightness has fallen far below the brilliance of ordinary stars. The importance of these objects as clocks becomes especially clear in globular clusters. A globular cluster is a dense, roughly spherical gathering of very old stars bound together by gravity. These clusters orbit the Milky Way and belong to some of its most ancient stellar populations. Many contain hundreds of thousands of stars packed into a relatively small region of space. Because most stars in a given cluster form around the same broad time, the cluster acts as a natural laboratory for stellar aging. Its stars differ mainly by mass, not by vastly different birth eras. This allows astronomers to compare stars at many stages of life within one ancient family. In such settings, white dwarfs become especially useful. By measuring how faint the coolest visible white dwarfs have become, astronomers can estimate how long they have been cooling, and from that infer the age of the cluster itself. The method rests on a simple principle. Hot white dwarfs are brighter. Older, cooler white dwarfs are fainter. In any ancient cluster, there is a lower edge to the brightness of the white dwarfs that can still be found. That lower edge reflects the cooling history of the oldest remnant stars in the cluster. If the cluster is younger, its white dwarfs have had less time to cool. If the cluster is older, the faintest ones have slipped farther down in brightness. This does not make the measurement effortless, because very faint stars are difficult to observe, and models of white dwarf cooling must be handled carefully. Even so, the method provides one of the clearest ways to estimate the ages of the oldest stellar systems near the Milky Way. In this sense, white dwarfs are quiet historians. They do not preserve the chemistry of the very early universe as directly as some metal-poor stars do. Instead, they preserve time through thermal decline. Their message is written in fading heat. This makes them especially powerful companions to other age measurements. A cluster's age can be estimated by studying the brighter stars that are just now leaving the main part of stellar life, and it can also be estimated by studying its coolest white dwarfs. When those lines of evidence agree, confidence grows. The cluster's antiquity becomes harder to dismiss as an artifact of one method alone. The oldest globular clusters, judged by such evidence, have ages reaching back to very early chapters of cosmic history, though still after the universe has already begun forming stars and assembling the first stable stellar populations. The white dwarfs themselves are also visually humbling. A brilliant star draws attention with ease. A white dwarf does not. It is small, faint, and often lost among brighter companions unless instruments are sensitive enough to isolate it. Yet this very modesty carries its scientific strength. These objects have no need for spectacle. Their value lies in steadiness. The laws governing how they cool allow their fading light to become a measure of time. In a universe where so many things change through collision, expansion, and violent birth, the white dwarf changes through quiet loss. It does not rush. It dims. Ancient white dwarfs also remind astronomy that visible age does not always announce itself in size or grandeur. One of the oldest things that can be seen may be a faint remnant in an old cluster, rather than some dramatic structure spread across space. Age often hides in what has endured the longest, not in what appears the largest. The white dwarf stage is a kind of endurance through reduction. The star is no longer what it once is, yet it still remains, carrying in its temperature the record of how much time has passed since its brighter life ends. So within the nearby universe, among old clusters and long-lived stellar populations, white dwarfs serve as some of the most delicate clocks available to sight. They are not the oldest visible light in transit, and they are not direct witnesses from the universe's first transparent moment. They belong to a later but still ancient chapter, when stars already exist, evolve, and leave behind remnants that cool almost without haste. In their faintness, age becomes measurable. In their slow decline, deep time remains visible. They stand as pale embers of vanished suns, and by studying how much heat they still retain, astronomy reads the long duration of some of the oldest stellar communities that can be directly seen near home. The Milky Way contains not only old stars but old structure. Its inner regions preserve a kind of fossil record, not in stone or bone, but in the ages, motions, and chemical makeups of stars that have remained bound to the galaxy through most of cosmic history. This record is not written in one place alone. It appears across the halo, the thick disk, the central bulge, and the ancient star clusters that orbit around them. Yet when these pieces are studied together, they reveal that the Milky Way is not a single smooth object formed all at once. It is an assembled system. Some of its oldest stellar populations preserve traces of the early phases of that assembly, when smaller structures merge, gas settles, and the young galaxy begins taking on a lasting form. In that sense, the Milky Way itself becomes a visible fossil, a present-day galaxy carrying inside it relics of its own beginnings. A fossil record in astronomy does not mean a perfect snapshot of one ancient moment. It means surviving evidence from early conditions. Stars can act as fossils because they retain memory in durable ways. Their orbits preserve the influence of earlier gravitational events. Their chemical composition preserves the state of the gas from which they form. Their ages preserve the sequence in which different galactic components emerge. A star that forms very early in the Milky Way, or in one of the smaller systems later absorbed into it, does not forget where it comes from in every respect. Time can scatter such stars across the galaxy, but it does not fully erase their patterns. Astronomy reads these patterns much as archaeology reads layers of a buried site. The medium is different, but the logic is similar. The past survives in arrangement. The halo remains one of the clearest repositories of this record. It surrounds the galaxy in a broad, diffuse sphere populated by old, metal-poor stars and ancient globular clusters. These are not arranged like the flat rotating disk where many younger stars and gas clouds are found. Halo stars often move on long, tilted and elongated paths. That difference matters. It suggests that the halo belongs to early and often violent stages of galactic growth, when the Milky Way gathers matter from many directions and incorporates smaller systems into a wider gravitational whole. Some halo stars appear to form within the early Milky Way itself. Others likely arrive from ancient dwarf galaxies that are drawn in and broken apart. Their remains do not vanish. They spread into streams, clouds, and populations that still trace the memory of those absorbed systems. The thick disk adds another layer of antiquity. It lies between the very old halo and the thinner, more actively star-forming disk familiar from many pictures of spiral galaxies. The thick disk contains older stars, greater vertical spread, and a different chemical pattern from much of the thin disk. This suggests that it belongs to an earlier stage of galactic settling, when the Milky Way is less orderly and more dynamically heated than it becomes later. The stars here are not as extreme in age or chemical simplicity as the oldest halo relics, yet they still preserve deep time. They help show that the Milky Way does not move directly from first assembly to modern calm. It passes through intermediate structures, each leaving behind a visible population. The central bulge carries another kind of fossil evidence. It is dense, crowded, and difficult to study because dust along the plane of the galaxy obscures much of the view in visible light. Even so, observations indicate that the bulge contains a large population of old stars. Many of them appear to form early, during intense phases of star formation and structural growth in the inner galaxy. Some parts of the bulge also show more complex histories, with stars of different ages and chemical signatures mixed together. This makes the bulge less like a simple relic locked in purity, and more like a layered ancient district that is built early, reshaped, and then inhabited across long spans of time. Its oldest stars still matter greatly, because they anchor the Milky Way's visible core to very early cosmic history. Chemistry gives this fossil record much of its power. A star formed from gas that has already passed through many earlier generations of stellar life tends to contain more heavy elements. A star formed earlier, from less enriched gas, tends to contain fewer. But the pattern is not only about amount. Different elements are produced on different timescales and by different kinds of stars. So the ratios between certain elements can reveal whether a star forms in a rapid burst of early star formation or in a more extended environment. This is why astronomers speak of galactic archaeology. They are not merely counting old stars, they are reading a coded record of formation history inside those stars. When age, orbit, and chemistry all point in the same direction, the past becomes more legible. The Milky Way's fossil core is therefore not one single object at the exact centre. It is a connected ancient record that becomes especially rich in the older populations of the inner galaxy and the surrounding halo. These stars remain visible now in the present sky. But many of them belong to a time when the galaxy itself is still young. Their existence shows that a galaxy can preserve pieces of its own beginning for billions of years. Those pieces do not remain untouched. They are stirred, absorbed into larger structures, and sometimes hidden behind dust or mixed with later populations. Yet enough remains for modern observation to reconstruct broad chapters of galactic birth and assembly. This is one reason the Milky Way is more than a backdrop for astronomy. It is also a nearby laboratory for the study of ancient cosmic history. Distant galaxies show early epochs through long-travelling light, but the Milky Way offers another route. It allows direct study of old stellar populations close enough for detailed measurement. Their individual motions can be tracked, their spectra can be analysed, their ages can be estimated with care. The galaxy becomes readable at the level of its constituent stars, and that detail gives unusual power to the local fossil record. So within the visible universe near home, the Milky Way stands as a structure that remembers its halo, thick disk, bulge, and old clusters preserve traces of early assembly. Ancient stars move through it as long-lived evidence of a formative age when the galaxy is still gathering itself into durable form. These are not the oldest visible signals in the universe by travel time, and they do not precede the first release of light into transparency. But they are among the oldest visible structures that can be examined in rich detail from within our own galactic setting. In them, the Milky Way ceases to be only the environment around Earth, and becomes instead an ancient artifact, still luminous, still changing, and still carrying the visible remains of its youth. Beyond the oldest visible stars near the Milky Way, the sky opens into a larger and stranger archive. It becomes a field of galaxies spread across immense depth, and in that depth, the relation between distance and age grows much more powerful. A nearby ancient star may be old in itself, but a distant galaxy brings something different. Its light has been travelling for such a long time that the galaxy appears not as it is now, but as it is during a far earlier age of the universe. This is the quiet importance of distant galaxies. They turn the sky into a record of cosmic history on the largest scale visible to telescopes. Each remote galaxy becomes a scene from an earlier era. The farther the galaxy lies, the earlier the visible chapter it reveals. A galaxy is not one star, but a vast collection of stars, gas, dust, and dark matter held together by gravity. Some are spiral, with disks and arms. Some are smooth and rounded. Some are irregular, less settled in form. Nearby galaxies can be studied in great detail, and their light shows a mature universe with long-developed structures. Farther out, the story changes. Because the light requires so much longer to arrive, distant galaxies often appear less settled, smaller, clumpier, and more active in star formation. This does not mean the laws of nature are different there. It means the galaxies are being seen during earlier stages of their growth. Distance becomes a method for reconstructing development. A galaxy far away is not only distant in space, it is young in the visible record. This is why astronomy treats remote galaxies as markers of deep time. The universe expands, and as it expands, the light travelling through it is stretched to longer wavelengths. This effect is called redshift. The term sounds technical, but the basic idea is simple. Light released long ago while travelling across an expanding universe arrives with its wavelengths lengthened. The more distant the source, in general, the greater this stretching becomes. By measuring that shift, astronomers estimate how far away a galaxy lies, and therefore how far back in time its light has been travelling. Redshift becomes a kind of time stamp. It does not give every answer by itself, but it tells astronomy where in cosmic history a visible galaxy belongs. This changes the meaning of observation. A telescope does not merely collect faint light from faraway places, it also arranges galaxies across time. Nearby galaxies show later stages of cosmic history. More distant galaxies show earlier stages. Very distant galaxies show the universe when it's only a small fraction of its present age. The sky, in this sense, becomes less like a flat map and more like a layered history. One region of a deep image can contain objects whose light begins its journey a few 100 million years ago, and others whose light begins its journey more than 13 billion years ago. They appear together in one field of view, but they do not belong to the same era. The telescope receives them in one moment on Earth, yet each one comes from a different age of the universe. There is also a visual humility in distant galaxies. What seems at first like a simple faint smudge often carries a vast history. A weak point of light in a deep survey image may represent billions of stars gathered into a young system in the remote past. The object appears small not because it lacks significance, but because distance has reduced its visible size and brightness. This is one of the most important habits astronomy learns. Apparent weakness is not the same as actual smallness or unimportance. In the distant universe, faint light often means great age in transit. The dimmest patches can belong to some of the earliest visible chapters of galactic formation. As distance increases, another change appears. Galaxies are seen not only earlier, but during a time when the universe itself is denser, hotter, and less developed in its large structures than it is now. The familiar modern arrangement of grand spiral disks, long-settled star populations, and richly enriched gas becomes less common. Earlier galaxies often appear more compact and irregular. Many are undergoing rapid star formation. Some seem to assemble through mergers and unstable bursts rather than through the calmer structure often seen nearby. This does not mean all early galaxies look alike, and it remains uncertain in many cases exactly how quickly different systems mature. But observations indicate that distant galaxies often present a universe still in the act of organizing itself. So galaxies through deep time offer more than distant scenery. They offer sequence. They allow astronomy to compare earlier and later cosmic ages directly by observing systems at different distances. Nearby galaxies can be placed beside intermediate ones, and those beside very remote ones, until a broad developmental picture begins to emerge. This method does not show one single galaxy evolving step by step across billions of years. Human observation does not last that long. Instead, it shows many galaxies caught at many different ages, from which the broader history of galaxy formation can be reconstructed. It is a comparative archive spread across the sky. This archive has limits. The farther astronomy looks, the fainter and more red-shifted the galaxies become. Their light grows harder to detect. Dust, intervening material, and the limitations of instruments all make the earliest galaxies difficult to isolate and confirm. Yet the principle remains steady. Every increase in reach extends visible time. Every successful detection at larger distance moves observation deeper into the past. In this way, distant galaxies prepare the way for the search for the oldest visible things, not because they always contain the oldest objects in themselves, but because their light allows the eye to enter earlier cosmic eras than nearby stars ever can. So at this level of the outward-to-inward journey, the universe appears as a grand procession of galaxies across time. Near ones speak from later ages, far ones speak from earlier ones. Their shapes, brightnesses, and redshifts together turn space into chronology. A galaxy at great distance is not just another island of stars. It is a visible fragment of a younger cosmos, preserved by the long travel of light. In that sense, the sky's farthest galaxies do not merely occupy the edge of space. They stand along the edge of the visible past, where the universe begins to show itself in earlier and earlier forms. Among the distant galaxies seen across deep cosmic time, a smaller and more demanding group stands nearer the beginning than the rest. These are the earliest galaxies now observed with the James Webb Space Telescope, visible from a period when the universe is only a few 100 million years old. They do not belong to the present shape of the cosmos. They appear from an age when galaxies are still small, dense, and rapidly forming stars. Their light has travelled for almost the full visible history of the universe before reaching Earth. And because of that long journey, they become some of the most ancient galactic scenes that can be directly observed. Yet even these remarkable systems are not the oldest light itself. They are early structures already formed within a universe that has been visible for some time. What Webb changes most clearly is not the basic meaning of distance, but the depth at which galaxies can be seen and confirmed. Earlier telescopes already reveal galaxies from very early eras, but Webb is built to work especially well in infrared light, where the stretched signals from the distant universe arrive. This makes it unusually powerful for detecting galaxies whose light begins its journey in the first few 100 million years after the Big Bang. As a result, astronomy now sees farther into galactic history than before, not in the sense of a vague promise, but in the form of specific observed systems whose distances can be measured with much greater confidence. Some of the galaxies now confirmed by Webb belong to times less than 300 million years after the beginning of cosmic expansion. Others belong to the range of roughly 300 to 500 million years. Together they bring the first visible age of galaxies into sharper view. These earliest observed galaxies are often compact in appearance. They do not usually show the wide, settled disks and grand spiral arms familiar from many nearby galaxies. They appear smaller, denser, and more concentrated, as though much of their visible activity is packed into tight regions. This does not mean they are simple. Even in youth, galaxies can contain rich internal processes, bursts of star formation, changing gas flows, and uneven structure. But the general impression differs from the more mature galaxies of later cosmic time. Webb's earliest systems often look like concentrated islands of light emerging from a young universe that is still building larger and more durable forms. Their brightness has also drawn attention. Some early Webb discoveries seem brighter or more developed than many astronomers expect before the telescope begins observing. This does not overturn the broad framework of cosmic history, but it does refine the picture. If galaxies appear abundant, bright, or chemically active at such early times, then some parts of galaxy formation may proceed faster or under denser conditions than simple older expectations suggest. Observations indicate that these young systems can form stars vigorously and may already contain elements produced by short-lived earlier stars. That point matters. A galaxy seen only a few 100 million years after the Big Bang is still very early. But it is not primordial in the absolute sense. By the time its light is released, stars have already formed, lived, and begun altering the gas around them. Even very early galaxies, therefore, belong to a universe already at work. Webb has also taught astronomy to be careful. Some of the earliest galaxy candidates identified in initial imaging later proved to lie somewhat nearer than first thought once more detailed measurements are made. This is a normal part of scientific progress, especially at the edge of detectability. Very distant galaxies are faint, highly red-shifted, and difficult to distinguish from other sources that can mimic similar colours in early surveys. For that reason, the strongest claims depend on spectroscopy, the splitting of light into its constituent wavelengths to measure redshift more securely. When that confirmation is obtained, the galaxies move from possibility toward firmer place in the cosmic timeline. So the early Webb era is not simply a race to announce ever more distant objects. It is also a process of sorting, checking, and narrowing uncertainty until the visible record of early galaxies becomes more stable. Within that process, a few names begin to stand out. Galaxies such as JADES-GS-Z 14-0 and MOM-Z14 represent some of the deepest confirmed steps into galactic time now visible, appearing from less than 300 million years after the Big Bang. They are not important because of their names alone, but because they show that galaxies already exist and shine from an astonishingly early era. Their light reaches Earth from a universe still in its first small fraction of life. This does not place them at the beginning of visibility itself, but it places them close enough to that beginning to make the young universe feel less abstract and more observationally real. There is calm but profound distinction here. The oldest galaxies Webb sees are among the oldest structured objects that can be directly observed with light. They are made of stars, gas, and growing complexity. They show that structure arises early, but they are still later than the release of the oldest observable glow across the sky. These galaxies form after the universe has already cooled far beyond its earliest visible state, after matter has separated into large-scale patterns, and after time has already passed long enough for stars to begin reshaping their surroundings. The earliest galaxies therefore do not answer the question of the oldest visible thing by themselves. They answer a narrower and very valuable version of it. They show how early an already formed galaxy can be seen. That is what gives this region of the subject its special place. It is a threshold between the familiar galactic universe and the even earlier cosmos that exists before galaxies are common. Webb's earliest galaxies stand at that threshold like the first settled lights visible beyond a deeper darkness. They are not yet the whole story of the young universe, but they are among the first rich structures that can be directly studied there. Their small sizes, intense star formation, and surprising maturity in some cases all suggest that the first chapters of galactic history are active, crowded, and fast-moving. So within the layered archive of the sky, Webb's earliest galaxies mark one of the deepest levels where structured cosmic objects are presently seen with confidence. They belong to the first few 100 million years after the Big Bang. They appear compact, vigorous, and young, yet already real as galaxies rather than mere hints of future structure. They reveal that by this early age the universe has begun building luminous islands of stars, and still, for all their antiquity, they remain later arrivals than the oldest light itself. They are early witnesses within the visible universe, not its first illumination. There is a frontier in the early universe that is not marked by a wall, a border, or a visible line across space. It is marked instead by a change in the state of the gas that fills the vast regions between galaxies. After the universe cools enough for neutral hydrogen atoms to exist, the great cosmic expanse becomes filled with matter that is no longer fully ionized. In simple terms, the electrons and protons that once move SSS. Neutral hydrogen interacts strongly with certain kinds of energetic light, especially ultraviolet light, and because of this the young cosmos becomes in large part opaque to that radiation. The universe is not dark in the sense of containing no matter. It is dark in the sense that light capable of passing cleanly across great distances is still limited by the state of the gas. The reionization frontier begins when that condition starts to change. Reionization means that neutral atoms are broken apart again into electrons and protons. The word sounds severe, but the process unfolds gradually, not all at once. It does not sweep through the universe like one single flash. It begins in scattered regions where the earliest sustained sources of energetic radiation form and begin altering their surroundings. Around those sources, patches of gas become ionized. Beyond them, large regions remain neutral for long periods. The early universe during this era is therefore mixed in condition. It is neither fully neutral as it is before, nor fully ionized as it becomes later. It is a patchwork. Some zones are transparent to energetic radiation. Others still absorb and scatter it. Reionization is the long transition between those states. This makes the frontier difficult to imagine in ordinary earthly terms. On Earth, change often appears through advancing edges that can be seen directly, such as a shoreline, a storm front, or the line of sunrise. In the early universe, the frontier is more like a widening network of clearings inside a fog. Each clearing grows around a source of radiation. Over time, neighboring clearings expand, touch, and merge. Regions once isolated begin to join into larger transparent volumes. Yet even this image is only approximate because the early universe is not uniform in density. Gas gathers more thickly in some places and remains thinner in others. Light escapes more easily from some environments than from others. So the spread of ionization depends on both the sources of radiation and the structure of the matter between them. The frontier is therefore irregular, textured, and deeply tied to the developing architecture of the young cosmos. At this stage, the universe is still simple in composition compared with later times. Hydrogen dominates. Helium is present as well. heavy elements are rare. The regions between galaxies, often called the intergalactic medium, contain much of this matter in diffuse form. Diffuse means thinly spread, not gathered into stars or planets. Even in that thinness, the gas matters greatly, because it is the medium through which early radiation must pass. A galaxy can shine, but if the surrounding hydrogen remains neutral and thick enough in effect, much of the energetic light is absorbed before it can travel far. That is why ionization is not only about the birth of luminous sources, it is about the struggle between emitted radiation and the neutral gas that surrounds and separates those sources. The transition also has a timescale that is long by human standards and gradual by cosmic standards. It extends across hundreds of millions of years. During this period, the universe becomes steadily more transparent, but not in one smooth and uniform way. Some observations indicate that by around 1 billion years after the Big Bang, much of the intergalactic hydrogen is already ionized across large cosmic regions. Earlier than that, the picture is less complete and more uneven. It remains uncertain in detail exactly how rapidly different regions clear, how much each class of source contributes, and how the process varies with local density and structure. But the broad scientific picture is stable. Reionization is a major transition in which the wider cosmic gas changes from mostly neutral to mostly ionized again. This matters because transparency changes what can move across the universe and what can be seen. When hydrogen is neutral, certain important wavelengths of light are strongly scattered or absorbed. When hydrogen is ionized, those barriers weaken. Radiation can travel more freely through intergalactic space. The universe becomes easier to see through. This is why the reionization frontier is not only a physical change in matter, but also a change in visibility itself. It reshapes the conditions under which cosmic light can cross distance. In a real sense, it opens the universe. The early cosmos goes from being wrapped in a widespread absorbing medium to becoming, over time, more transparent to the radiation passing through it. There is a quiet grandeur in this process. Nothing about it depends on one dramatic event seen from one privileged position. It unfolds everywhere and nowhere at once, through countless local changes that add up to a new cosmic condition. The young universe is not instantly illuminated in one universal sunrise. It is altered in pieces. Bubbles of ionized gas expand. Neutral regions retreat. Light gains ground gradually. The process belongs to the large-scale environment between galaxies rather than to any single object alone. That is why this frontier deserves its own place in the outward-to-inward path. It is a region of transition, broad and environmental, neither the first appearance of sources themselves nor the deeper earlier universe before such clearing begins. It is also a frontier because it marks the boundary of a changing observational world. When astronomers detect signs that a very early galaxy sits within or near a locally cleared region, they are seeing evidence that reionization is not merely an abstract epoch on a timeline. It is a lived condition of the early universe, with transparent pockets, lingering neutral gas, and uneven cosmic weather shaped by radiation and matter. The universe during this era is neither fully hidden nor fully open. It exists between those states, and that in-between character is exactly what gives the frontier its meaning. So reionization stands as one of the great environmental transitions in cosmic history. The young universe, once filled with mostly neutral hydrogen after its early cooling, begins to change under the influence of energetic light. Clear regions form within a wider fog. Those regions grow, overlap, and gradually turn the intergalactic medium into a more ionized and transparent state. This is not yet the oldest visible light. nor is it the earliest possible phase of the cosmos. It is a later threshold, but still an ancient one, where visibility itself is being remade across the vast spaces between galaxies. The frontier is not a line to cross, but a condition to enter, and within it the early universe slowly clears. Before galaxies become common, and before the wider universe clears in large patches, there comes a quieter and more decisive turning point. The first stars appear. Their arrival does not yet produce the mature cosmic scenery seen in later ages. It does not fill the sky with settled galaxies or richly structured systems. It begins instead with isolated sources of light forming within the universe still young, simple, and thinly enriched. These first stars matter because they mark the end of a long interval without stellar illumination. They introduce sustained starlight into a cosmos that until then contains matter, motion, gravity, and growth, but no true stars. In that sense, they are the first lamps of the post-Big Bang universe. Their birth depends on cooling and collapse. After the universe expands and cools from its early hot state, matter does not remain perfectly smooth. Tiny differences in density already exist. Some regions contain slightly more matter than others. Gravity acts on those differences across immense spans of time, drawing gas into denser pockets. The gas is mostly hydrogen, with helium as the next major ingredient. Heavy elements are effectively absent at this stage. That absence is important. In later cosmic eras, heavier elements and dust help gas cool more efficiently, allowing clouds to fragment into many smaller pieces. In the first era of star formation, that cooling is more limited. The gas must rely on simpler processes, including the formation of small amounts of molecular hydrogen, to shed heat and continue collapsing. This changes the character of the first stars from the beginning. Observations and simulations indicate that the earlier stars are likely different from many stars formed later. Without heavy elements to aid cooling and fragmentation, the first star-forming clouds tend to produce stars that are, on average, much more massive than the Sun. Massive does not mean merely somewhat larger. It can mean tens or even hundreds of times the Sun's mass, though the exact range remains uncertain and may vary from one environment to another. Current evidence suggests that the earliest stellar populations are often dominated by large, hot, luminous stars, while also leaving open the possibility that some lower mass stars form in at least a fraction of cases. What remains clear is that these first stars are not expected to resemble the typical quiet stars that dominate many nearby regions of the Milky Way. Because they are massive, they live quickly. A star's lifetime depends strongly on its mass. The greater the mass, the faster it consumes its nuclear fuel. So the first stars, though brilliant, are short-lived. They burn intensely for only a few million years before reaching the end of their lives. This gives their appearance a striking character in cosmic history. They arrive after a long period without stars, yet each individual one may live only briefly. Their importance does not come from long survival. It comes from firstness and from effect. They are the first stable furnaces to shine in the cosmic dark. Their light is harsh by later standards. Massive young stars produce large amounts of ultraviolet radiation. This energetic light begins changing the gas around them almost at once. Nearby hydrogen becomes ionized. Small cleared regions form in the surrounding medium. In this way, the first stars begin more than illumination. They begin transformation. Their radiation reshapes the local universe, heating and ionizing gas that until then remains largely neutral. Even before large numbers of galaxies develop, the first stars start the process of turning a quiet, neutral cosmos into one more transparent and altered by light. They also begin chemical change. The universe before the first stars is chemically simple. It contains mainly hydrogen and helium, with only trace remnants of a few lighter elements formed in the earliest minutes after the Big Bang: carbon, oxygen, iron, and the many other heavier elements familiar to planets, rocks, atmospheres, and life do not yet exist in meaningful abundance. The first stars become the first major makers of such elements. Deep within their hot interiors, fusion creates heavier nuclei. When these stars end their lives, some explode violently and cast newly made elements outward into surrounding space. Others may collapse more directly into black holes, contributing less enrichment to the medium around them. The details depend on mass and internal physics, and some of those details remain uncertain. But the broad picture is steady. The first stars begin the chemical enrichment of the universe beyond its original simplicity. This is why they are so important, even though none has yet been directly seen as an individual confirmed star. Their presence is inferred from theory, from simulations grounded in known physics, and from later observational consequences. The early enrichment of gas, the emergence of radiation capable of ionizing the surrounding medium, and the need to explain the first luminous phases of the universe all point toward an initial generation of stars unlike later ones. Astronomers often call these first stars population 3 stars. The label is historical rather than intuitive. It simply designates the earliest generation, formed before the universe is substantially enriched by stellar recycling. The name matters less than the concept. These are the first true stellar sources in cosmic history. There is a particular quietness in this beginning. The first stars do not rise over landscapes. They do not appear against familiar skies. They ignite within a universe that still lacks most of the structures now taken for granted. There are no mature galaxies with long-formed disks. There are no planets known to circle them in the rich chemical sense familiar later. There is mostly dark space, diffuse gas, and the first gravitationally gathered nurseries capable of collapse. Into that setting, a star ignites. The event is profound not because it is publicly visible from some grand vantage, but because it changes what the universe contains. Before, there is no starlight. After, there is. Their existence also marks a threshold in what can later be seen. Once stars form, they create radiation, heat, structure, and heavier elements. They become the seeds of later galaxies, later generations of stars, and later worlds. Yet in this section they must remain only themselves, not yet the galaxies that will house many later stars, not yet the broader cleared universe that expands under cumulative radiation. Only the first stellar sources, appearing in a simple cosmos and establishing a new category of thing. The universe begins with expansion, particles, nuclei, atoms, and diffuse matter. Then at last it acquires stars. So the first stars stand as the earliest sustained makers of visible starlight after the universe's hot beginning, formed from nearly pure hydrogen and helium, likely massive, hot, and short-lived. They ignite within collapsing pockets of primordial gas and immediately begin altering the regions around them. They create the first ultraviolet radiation from stars, the first strong local ionized zones, and the first major wave of chemical enrichment through their deaths. Though they probably do not survive to the present and have not yet been directly isolated one by one, their role in cosmic history is foundational. They are the first lamps in the long night, and with them the universe passes from darkness with matter into darkness that has begun to shine. After the first release of ancient light has long passed, and before the first stars begin to shine, the universe enters an interval of extraordinary quiet. This interval is often called the cosmic dark ages, The name does not mean that nothing exists. It does not mean that space is empty or that time has paused. Matter remains present everywhere in diffuse form. Gravity continues working without interruption. The universe still expands. Tiny differences in density continue to grow slowly under their own attraction. Yet for a long span there are no stars, no galaxies filled with luminous structure, and no sustained visible sources of light crossing the darkness. The cosmos is active in a hidden way, but not yet radiant in the familiar sense. It contains the conditions from which later light will arise, while remaining itself largely unlit. Darkness here must be understood carefully. The universe is not dark because all light has vanished in the absolute sense. The older background glow released much earlier still exists and still fills space, though by this era it has cooled and shifted far beyond visible wavelengths. That ancient radiation remains present as a bath of weakened energy across the cosmos. But in terms of visible or near-visible luminous structure, the universe is quiet. There are no stars yet to mark regions of space with steady points of brilliance. There are no galaxies yet assembled into obvious islands of light. What exists is a wide and expanding medium of matter in which the future luminous universe is still only a possibility taking shape through gravity. Darkness therefore means the absence of discrete luminous objects, not the absence of physical reality. This makes the Dark Ages one of the most difficult cosmic eras to imagine. Human understanding of darkness usually depends on nearby experience. A room is dark because a lamp is off. A landscape is dark because the sun has set. In such cases, the surrounding world is already fully formed and simply not illuminated at the moment. The cosmic Dark Ages are different. The universe is not a finished landscape waiting for dawn in the ordinary sense. It is a young and still developing cosmos in which the principal sources of later illumination do not yet exist. There are no stars hidden behind the horizon. There is no earlier civilization of galaxies waiting to reappear. The darkness belongs to origin, not interruption. It is the darkness of a universe before stellar light becomes part of its structure. Time during this era is measured not by clocks in any familiar sense, but by the changing conditions of matter and the gradual growth of structure. Tiny irregularities already present in the early universe, visible much earlier in the ancient glow across the sky. Do not disappear. They persist as slight overdensities and underdensities in the cosmic matter field. Gravity acts on those small differences across millions of years. Slightly denser regions draw in more matter. Slightly emptier regions fall further behind. The process is slow, especially in the ordinary matter that later forms stars, because that matter is still diffuse and spread thinly across expanding space. Yet the Dark Ages are not motionless. They are formative. The quiet is not emptiness of process. It is the absence of visible flame while hidden gathering continues. The universe during this time is also simpler than it becomes later. It has not yet been greatly altered by stars, stellar winds, or explosions. No previous generations of suns have forged and scattered heavy elements into space. No planets circle mature stellar systems. No dust-rich clouds drift through well-formed galactic disks. The later universe becomes chemically and structurally complex because stars make it so over time. During the Dark Ages, that work has not yet begun. The cosmos remains close to its early simplicity, dominated by the basic ingredients left from the first stages of cosmic history, and by the silent influence of gravity drawing matter into denser patterns. That simplicity gives the Dark Ages a certain purity. It is one of the last eras before the universe fills with its own internally generated light. Once stars appear, everything begins to change. Radiation heats surrounding gas. Heavy elements begin to form and spread. Galaxies start to develop and interact. Later chapters of cosmic history become richer, brighter, and more complicated. The Dark Ages stand just before that transformation, in a condition where the universe is still largely defined by primordial matter, expansion, and the slow amplification of tiny initial differences. It is a threshold era, but here it must remain only itself. Not yet the first stars, not yet the cleared cosmic regions shaped by radiation, only the prolonged interval in which the universe has not yet lit its first lamps. This era also reveals something important about visibility. There are parts of cosmic history that do not announce themselves through bright objects. Some epochs must be understood through background conditions, later consequences, and the physics of matter before visible structures exist. The Dark Ages belong to this category. It is one of the least directly theatrical phases in the universe, yet it is essential. Without it, the first stars would have no time to emerge from growing density patterns. Without it, the universe would leap unrealistically from early transparency to mature luminosity. The Dark Ages are the quiet incubation between those conditions. They allow space, time, and gravity to do slow work before light returns in a new form. The emotional force of this era comes from its calm scale. The darkness is not local, it is nearly universal. It stretches across all regions not yet touched by future stars because there are as yet no such stars anywhere. The universe contains matter everywhere, and silence everywhere in the luminous sense. Even that statement must be treated carefully, because sound in the earthly sense has no place in the vacuum that later becomes widespread between structures. Yet the image of silence still helps. It suggests a cosmos present but not yet speaking through stars. The Dark Ages are a period when reality exists in full, but has not yet taken on the bright visible forms that later dominate human imagination of the universe. Astronomy reaches toward this era with difficulty because it offers so little direct visible structure. It must be reconstructed through theory, through the imprint of earlier and later states, and through careful attempts to detect faint signals from the matter that fills this time. The broad outline is well supported. After the early universe becomes transparent, and before the first stars begin sustained shining, there is a prolonged dark interval. Its exact timing can vary somewhat depending on how one defines the first widespread stellar birth, and how early one counts the first luminous objects. But the general reality of the Dark Ages remains secure. It is the universe without stars, expanding and evolving in preparation for them. So the cosmic Dark Ages stand as one of the purest intervals of hidden becoming in all cosmic history. The universe is already real, already structured in seed form, already governed by expansion and gravity, but not yet illuminated by stars or galaxies. Ancient background radiation still exists, but no discrete stellar sources yet punctuate the dark. Matter gathers slowly. Time passes immensely. Complexity waits inside simplicity. This is not the end of a light, but the interval before starlight begins. In that long quiet, the universe holds its breathless early form, not empty, not still, but unlit in the way only a young cosmos can be. During the cosmic Dark Ages, the universe is not empty between future stars and galaxies. It is filled above all with hydrogen. This hydrogen does not appear as bright clouds drifting across a lit background. It does not gather into the kind of visible forms later associated with nebulae or stellar nurseries. It exists instead as a vast, diffuse sea spread through almost all of space, thin in any local sense yet immense in total extent. This sea of matter is one of the most important realities of the young universe. It supplies the raw material from which later stars and galaxies grow, and it also shapes what kinds of radiation can or cannot pass across the cosmos. During this era, hydrogen is not simply present. It defines the large-scale character of visible absence. Hydrogen is the simplest atom. In its neutral form, it consists of one proton with one electron bound to it. Neutral means the positive and negative charges balance each other. In the earlier, hotter universe, matter does not remain arranged in stable neutral atoms because temperatures are too high and radiation too intense. Electrons move freely, and light interacts constantly with the ionized matter. Later, as the universe expands and cools, electrons and protons combine into neutral atoms in great numbers. Once that change occurs, the matter-filling space becomes very different in how it interacts with radiation. The early universe enters a period when neutral hydrogen dominates the ordinary matter between future structures. That dominance continues through much of the Dark Ages. This hydrogen sea is not uniform in a perfect sense. Tiny differences in density remain from earlier cosmic history. Some regions contain slightly more matter than average, others contain slightly less. At first, these differences are very small, but gravity acts on them patiently. Over immense spans of time, denser regions pull in more material, while thinner regions become emptier by comparison. The hydrogen sea therefore carries the seeds of later structure within it. It is not a smooth sheet laid across the universe. It is a gently uneven medium, almost featureless to ordinary thought, yet quietly shaped by patterns that will eventually matter enormously. The future brightness of stars and galaxies begins here, not as visible light, but as slightly uneven distribution. The thinness of this sea is difficult to picture. Even where hydrogen fills the universe, it is not packed like air near Earth's surface or water in an ocean. The word sea helps describe continuity and extent, not density. The gas between future structures is extraordinarily diffuse. Individual atoms lie far apart by earthly standards, yet because the universe is so vast, this sparse material still constitutes an enormous total reservoir of matter. Nearly all directions through space lead through it. It is the great background substance of the young cosmos, the medium in which later luminous structures are embedded. The universe at this stage is therefore not made of bright islands floating in empty nothingness. It is made of a thin, nearly universal hydrogen medium within which brighter structures have not yet widely formed. Its neutrality matters deeply because neutral hydrogen interacts strongly with certain wavelengths of light, especially those associated with electronic transitions in the atom and with energetic ultraviolet radiation. This means that even though the universe is transparent enough for the ancient background glow to travel across it, it is not equally transparent to all later radiation. Neutral hydrogen can absorb, scatter, and reshape light in ways that affect visibility. During the Dark Ages and the early stages of reionization, this hydrogen sea limits how far energetic radiation can pass before being absorbed. The young universe is therefore not only a matter-filled environment, it is an optical environment with specific rules. What can be seen? What can travel freely? And what becomes trapped or transformed all depend partly on the condition of this diffuse hydrogen. The sea also cools with time. As the universe expands, the average energy of the gas declines. Expansion stretches wavelengths, lowers densities, and reduces the frequency of interactions. The hydrogen does not sit in one static thermal state. It evolves with the wider expansion of the cosmos. At first, it remains more closely tied to the surrounding radiation field. Later, its temperature history diverges more strongly as the universe grows older and thinner. This changing thermal state affects how the hydrogen can be detected in principle, and how it responds to later light from the first stars. Even before stars exist, the gas is not inert. It is cooling, drifting, and slowly deepening the density patterns from which future structure will emerge. There is another quiet importance in hydrogen's simplicity. Because it is so simple, it becomes a powerful tracer of early cosmic conditions. Later stages of the universe are full of chemical complexity, heavy elements, dust grains, magnetic activity shaped by stars, and violent feedback from galaxies all complicate the picture. During the Dark Ages, most of that later richness does not yet exist. The dominance of neutral hydrogen means the ordinary matter of the universe remains close to primordial simplicity. This gives the era a stripped-down character. The cosmos is governed by a few major ingredients and processes rather than many: hydrogen, gravity, expansion, and the residual effects of earlier radiation together shape most of what matters in the visible absence of this age. The hydrogen sea is also what makes the later arrival of starlight so transformative. When the first stars ignite, their radiation does not enter an empty stage. It enters this widespread neutral medium. Their light must carve into it, heat it, ionize it, and alter it locally before broader cosmic change can follow. The first luminous sources gain significance partly because of what surrounds them. Against an already bright and transparent universe, their emergence would mean something different. Against a universe filled with diffuse neutral hydrogen, their emergence becomes the beginning of a struggle between light and matter. The sea is therefore not passive background. It is the medium that gives later illumination its physical consequences. Even in the absence of visible form, this hydrogen-filled universe is not without structure in principle. The slight density variations, the gradual inward pull of gravity, and the thermal history of the gas all create a hidden landscape. It is hidden because ordinary visible objects are not yet present to outline it. There are no bright boundaries, no glowing clouds easily seen by eye, no stellar beacons to mark the denser regions. Yet the landscape exists. The hydrogen sea is already folding very gently toward future complexity. It contains the map of what will later become more obvious. Matter is there before form becomes luminous. So the neutral hydrogen sea of the Dark Ages stands as one of the most essential and least dramatic regions of cosmic history. It fills the universe in diffuse simplicity. It carries tiny variations that gravity slowly amplifies. It governs how later radiation can move across space. It cools with expansion and preserves a young cosmos still close to its original chemical condition. There are no visible stars yet marking this medium from within, and so it remains a universe of matter without luminous form. But the absence of visible structure does not mean the absence of meaning. In the vast thin spread of neutral hydrogen, the early universe holds the raw material, the hidden landscape, and the quiet optical barrier from which later cosmic light will emerge into view. Across the whole sky there is a glow that does not belong to any star, galaxy, or cluster of galaxies. It comes from every direction at once. It does not gather into points. It does not trace the outlines of visible structures. It surrounds all later cosmic scenery as a faint and nearly uniform background. This glow is called the cosmic microwave background. The name sounds technical, but its meaning is simple. It is ancient radiation filling the universe, now cooled so greatly by cosmic expansion that it arrives mainly in the microwave part of the spectrum rather than as visible light. It is the oldest light that can be directly observed, not the oldest object that still shines. not the oldest star, not the earliest galaxy. It is older than all of those as visible evidence. It is the deepest layer of light the universe still allows astronomy to see. This glow is not dramatic to human sight because human eyes cannot detect microwaves. If a person stands beneath the night sky, the ancient background is present above and through that sky, but it is invisible to ordinary vision. Special instruments are needed to receive it. Radio and microwave telescopes, along with sensitive detectors carried on balloons, spacecraft, and observatories, can map its presence across the heavens. Once measured, the glow reveals itself not as a local signal from one place, but as a nearly universal bath of radiation. It is everywhere. This everywhere matters. A distant galaxy occupies one region of the sky. A star occupies one point. The microwave background fills all directions and stands behind every later visible structure, like a quiet, luminous sea stretched across the whole observable universe. Its faintness is one of its great signs of age. Long ago, the radiation is far hotter and more intense. Over billions of years, as the universe expands, the wavelengths of that light are stretched and its energy declines. What once belongs to a much hotter cosmic state arrives now as a glow only a few degrees above absolute zero. Absolute zero means the lowest possible temperature, the point at which thermal motion is reduced as far as nature allows. The microwave background remains slightly above that limit, which is why it still exists as measurable radiation. Its present temperature is extremely cold, yet not zero. That tiny surviving warmth is one of the most delicate and profound traces of the early universe. The sky is not merely dark, it is faintly warm with ancient light. The glow also appears astonishingly uniform. If the universe is surveyed in microwave light, the background looks almost the same in every direction. This smoothness reveals something essential about the early cosmos. It shows that the observable universe, on the larger scales visible in this radiation, begins from a state of remarkable evenness. Not perfect sameness, but near sameness. The background is one of the strongest pieces of evidence that the young universe is once hot, dense, and broadly uniform before later structures such as galaxies and clusters grow into their present forms. When astronomy measures this glow, it is not only collecting an old signal, it is examining the broad condition of the universe at an extraordinarily early time. This is why the microwave background occupies such a special place in the question of the oldest thing that can be seen. Other visible objects can be ancient in themselves, or their light can travel for immense spans. But the microwave background comes from a time earlier than the birth of stars and galaxies. It is not the light of mature structure. It is the afterglow of a young universe before later luminous objects dominate the cosmic scene. In terms of directly observed light, no star can outrun it in age. No galaxy can outrun it in age. The background is the deeper visible flaw beneath them all. Its discovery changes modern cosmology because it provides a direct observational link to the hot early universe. Before such a glow is found, the idea of a hot beginning has strong theoretical support, but the detection of this all-sky radiation turns that framework into something measurably concrete. The sky itself contains the remnant. It can be mapped, compared, and studied in detail. The glow is not a decorative addition to cosmology. It is one of its foundations. It reveals that the early universe leaves behind not only matter and later structure, but also a surviving field of ancient light that remains present around all later things. The microwave background also has a strange emotional quality. It is older than any visible star and older than any confirmed galaxy. Yet it is not hidden in one unreachable corner of the universe. It is here, surrounding Earth at every moment. Every observation of the sky takes place inside it. It passes through space near every planet, every cloud, every telescope. The oldest directly visible light is not remote in the sense of occupying one distant location. It is remote in time and universal in presence. That combination makes it feel unlike ordinary objects of astronomy. A far galaxy can be imagined as a place. The microwave background is not a place. It is a condition of the observable universe itself, a nearly omnipresent relic still arriving from the deepest visible past. Even its near uniformity carries meaning beyond simplicity. If the glow were wildly uneven, the young universe would appear chaotic on large scales. Instead, its broad smoothness shows that the primordial cosmos is controlled and coherent in a deep way. Later structures grow from this near-even beginning. The great complexity of the present universe, with its stars, galaxies, and clusters, emerges from a background that initially appears calm and almost featureless. The microwave background therefore stands at a subtle threshold. It is ancient light that is already free enough to cross the cosmos, yet it belongs to a universe not yet shaped into the rich visible architecture familiar later. So when the question asks for the oldest thing that can be seen, the answer at the level of direct light is not an old star in the Milky Way and not one of Webb's earliest galaxies. It is this faint microwave glow filling the sky. It is ancient radiation cooled by expansion, measurable in every direction, nearly uniform across the heavens, and older than all later luminous structures. It is the oldest light still available to observation. The night seems dark, but behind every visible point and every galaxy field lies this deeper radiance, patient and all-encompassing. The universe remembers its early visible state through it, and by receiving that faint glow, astronomy looks farther back than any star or galaxy alone can carry the eye. The oldest light that can still be observed does not come into freedom at the first instant of the universe. It is released later, after a crucial change in the condition of matter. For a long early stretch, the universe is too hot and too crowded for light to travel cleanly across it. Electrons move freely rather than remaining bound into neutral atoms. Protons also move freely, and photons, the particles of light, do not pass through such a medium without interruption. They scatter again and again from charged particles, changing direction constantly. The young universe during this state is bright in a deep physical sense, filled with radiation, but it is not transparent. Light exists everywhere, yet it cannot travel far without being deflected. The cosmos is like a luminous fog, not dark, not empty, but closed to long, direct sight. This condition changes as expansion continues. Expansion makes the universe larger, thinner, and cooler. Temperature falls because energy is spread across increasing space, and because the wavelengths of radiation stretch with the growth of the cosmos. Slowly, the environment moves toward a threshold at which electrons and protons can remain bound together, instead of being torn apart immediately by the surrounding radiation. When that threshold is crossed on a cosmic scale, ordinary neutral hydrogen begins to form in great numbers. The process is often called recombination. The word is not fully intuitive, because it suggests the joining again of things that are being united for the first time in this lasting way. Still, the meaning is straightforward. Free electrons settle into stable partnership with nuclei. Matter becomes neutral on a vast scale. This change has an enormous consequence for light. A universe full of free charged particles is highly effective at scattering photons. A universe filled largely with neutral atoms is much less so. Once electrons are no longer moving freely in such great numbers, the constant deflection of light drops sharply, the fog thins. Photons that have been trapped in countless interactions are suddenly able to travel much farther without being scattered. In effect, the universe becomes transparent. This does not mean perfectly empty or perfectly clear in the later modern sense. It means clear enough that ancient light can at last begin the long, uninterrupted journey that continues to the present day. The oldest directly observable light is therefore not created in that exact moment from nothing. It is released from confinement. It is ancient radiation set free. This threshold occurs when the universe is about 380,000 years old. By the standards of human history, that is beyond all familiar scale. By the standards of cosmic history, it is extremely early. The universe at that time is still young beyond comparison with its present age. No stars yet shine, no galaxies yet fill the darkness with structured light, no planets or heavy rocky worlds exist. The cosmos consists mainly of hydrogen, helium, dark matter, radiation, and the continuing framework of expansion. Yet at this moment something decisive happens. The universe becomes see-through to its own ancient light. That is why the release matters so profoundly. It marks the earliest visible surface available to direct observation. The phrase visible surface helps, though it must be used carefully. The universe does not possess a hard shell surrounding everything like the surface of a planet. The surface is one of visibility, not one of solid material. When astronomy looks into the microwave background, it is effectively seeing back to the epoch when the universe last scatters the radiation now arriving at Earth. Before that time, light cannot cross the plasma-like early medium freely enough to preserve a clear direct view. After that time, much of it can. So the oldest light appears to come from a kind of horizon, a boundary beyond which ordinary electromagnetic sight cannot move further back. The barrier is not distance alone, it is opacity in the earlier universe. The term last scattering is often used for this reason. Scattering means the deflection of light by matter. Last scattering refers to the final major interaction between the background photons and the charged particles of the early universe, before those photons stream onward through expanding space. The phrase captures the turning point with unusual precision. For immense stretches of early time, a photon does not possess a clear independent path. It is absorbed, re-emitted, or redirected over and over. Then the environment changes enough that one scattering becomes, for many photons, the last significant one. From there the path opens. The light that reaches instruments today begins that free journey at the moment when the cosmos ceases to be an imprisoning glow and becomes an open medium. There is a quiet inevitability in this transformation. No external agent arrives to clear the universe. No later stars burn away the fog. The change comes from the universe's own expansion and cooling. The very growth of space makes transparency possible. Matter and radiation, once tightly coupled, begin to part ways in their behavior. Radiation decouples from ordinary matter, meaning it no longer remains trapped in constant interaction with the charged particles around it. Matter continues evolving toward later structures. Radiation moves outward freely. This separation gives the universe a new kind of history. From this point onward, ancient light can survive as a messenger from the past. The conditions of the universe at release remain extraordinarily simple compared with later ages. There are no richly developed chemical environments, no dust-filled galaxies, no long cycles of stellar birth and death. The light being freed comes from a cosmos still close to primordial simplicity. That simplicity is part of why the released radiation is so important. It carries information from a young universe before later complexity overwhelms the basic conditions of origin. The oldest observable light is valuable not only because it is old, but because it belongs to a moment when the cosmic environment is still elementary, broad, and nearly uniform. Yet this moment is not the beginning of everything. Older phases exist. Before transparency, the universe is even younger, hotter, denser, and more opaque. Earlier events shape what this released light later carries. But those earlier phases cannot be directly seen with ordinary light because the medium does not allow photons to preserve a clean line of sight from there to now. This is why the moment of release holds such a privileged place. It is the first epoch from which light can reach the present without being erased into opacity by the earlier plasma. The universe may have deeper ages behind it, but direct luminous sight begins here. So the oldest observable light is born into visibility when the universe cools enough for neutral atoms to form and for photons to travel freely at last. About 380,000 years after the Big Bang, the early cosmic fog thins on a universal scale. Recombination turns a charged, scattering medium into a far more transparent one. Last scattering marks the final major deflections before the ancient radiation begins its immense, uninterrupted passage through space and time. This is the release point of the cosmic microwave background, the moment when the young universe first allows its own early light to escape into the long future. What is seen today as a faint microwave glow begins there, in the instant when the cosmos becomes clear enough to remember itself in light. At first glance, the cosmic microwave background appears almost perfectly uniform. It fills the sky with a near-even glow, and that smoothness is one of the strongest signs that the early universe is broad, hot, and remarkably similar from place to place on the larger scales. Yet the glow is not absolutely smooth. Embedded within it are minute variations in temperature, so small that they do not alter the overall calm impression, but real enough to carry some of the most important information in all of cosmology. These slight differences are often called anisotropies, a word that simply means that the radiation is not exactly identical in every direction. The departures from sameness are tiny, but they matter enormously. They are the first directly visible signs of the unevenness from which later cosmic structure grows. The size of these ripples is extraordinarily small. The average temperature of the microwave background is only a little above absolute zero, and the variations from one region of the sky to another are smaller still by a very large factor. The differences are measured in millionths of a degree. That scale of variation is so delicate that it lies far beyond anything human senses can notice directly. Only highly sensitive instruments can map it. Yet the smallness is part of the meaning. The early universe is not wildly clumped or chaotic. It is almost smooth, with only faint irregularities scattered across the whole sky. Those irregularities are enough. Gravity does not require dramatic initial contrast to build later structure. It can act over immense spans of time on very slight differences, drawing matter into denser regions and leaving emptier regions behind. In this way, the ripples in the ancient glow become visible seeds. The word seed is useful because it suggests potential rather than completion. A seed is not yet a tree, but it contains the beginning of one. The temperature variations in the microwave background are not yet galaxies, clusters, or cosmic webs. They are the first directly observed traces of the uneven conditions from which such things later emerge. Slightly warmer and cooler spots in the background correspond to subtle differences in density and motion in the young universe. These differences are present when the ancient radiation is released, and they preserve a map of where matter is just slightly more concentrated or slightly less concentrated than average. Later, cosmic history grows from that gentle imbalance. The relationship between temperature and density is not perfectly simple in every detail, because the early universe contains a tightly linked mixture of radiation, ordinary matter, and dark matter, all interacting through gravity and, in the case of ordinary matter and radiation, through pressure as well. Even so, the broad meaning remains clear. The microwave background does not merely show that the universe is old and once hot, it also shows that the young universe is structured in embryo. The glow carries a pattern. The pattern is faint, but it is not random noise imposed by instruments. It is real information from the early cosmos. What makes this especially striking is the contrast between the smallness of the ripples and the vastness of what later emerges from them. Today the universe contains galaxies with hundreds of billions of stars, clusters of galaxies, huge filaments stretching across intergalactic space, and wide cosmic voids where fewer galaxies gather. All of that visible richness grows, in part, from initial differences that are astonishingly slight. The microwave background allows astronomy to see those differences at a stage when the universe is still young, simple, and mostly smooth. It is therefore one of the clearest demonstrations that cosmic complexity does not require a dramatically uneven beginning. It can unfold from delicate irregularity, amplified patiently by gravity over billions of years. The sky map of these ripples also has structure of its own. The variations are not arranged as one large hot side and one large cold side. They occur across many angular scales, from broader regions down to finer patches. This distribution matters because it reflects the physical conditions of the young universe before and during the release of the ancient light. Ordinary matter and radiation in that era behave like a coupled fluid, with gravity pulling inward while radiation pressure resists compression. The result is a pattern of oscillations, sometimes described as sound-like waves in the early plasma. Sound here must be understood carefully. It does not mean sound travelling through open vacuum as it does not on Earth. It means pressure waves moving through the dense early medium. These waves leave an imprint in the microwave background, shaping the sizes and strengths of the temperature variations seen across the sky. Because of this, the ripples are not only seeds of later structure, they're also records of early physical conditions. Their pattern reveals how much ordinary matter exists, how much dark matter contributes to gravitational structure, how geometry operates on cosmic scales, and how the early universe behaves while matter and radiation are still closely linked. In other words, the tiny variations are both historical and diagnostic. They show what is there and how it behaves. The oldest directly visible light is not a blank wall, it is a finely textured record. There is something quietly humbling in the fact that the first visible structure in the universe appears not as brilliant objects, but as minute departures from uniformity. One might expect the earliest visible clues to be grand or dramatic. Instead, they are subtle. The universe first shows its future complexity through tiny wrinkles in an otherwise smooth glow. A slightly warmer patch, a slightly cooler patch, a delicate pattern spread over the whole sky. These modest contrasts are the earliest visible architecture of later creation. Before galaxies shine, before stars light their surroundings, the future universe exists in this muted form, written as faint unevenness in ancient radiation. The study of these ripples also changes the meaning of observation itself. Astronomy is not only looking at old light, it is reading structure in old light. The microwave background becomes more than an afterglow. It becomes a map of primordial conditions. one precise enough to compare with later observations of galaxies and large-scale cosmic structure. When those later structures are examined, they are found to be consistent with growth from the small fluctuations seen in the background. This link between the early ripples and the later universe is one of the great achievements of modern cosmology. It connects the nearly featureless young cosmos to the richly structured present one without requiring a break in physical law. So the tiny temperature variations in the cosmic microwave background stand as the first directly visible seeds of all later large-scale structure. They are minute in size, measured in millionths of a degree, yet immense in consequence. They show that the ancient glow is not perfectly uniform, but gently patterned. They preserve slight differences in density and motion from the young universe, and those slight differences later grow under gravity into galaxies, clusters, filaments, and voids. In these wrinkles of the afterglow, the future visible universe first appears, not yet in objects, but in possibility. The oldest light does not merely illuminate the early cosmos, it carries the first faint blueprint of what the cosmos will become. The ancient glow across the sky does not carry only temperature and brightness. It also carries orientation. This subtler property is called polarization. In simple terms, polarization describes the preferred direction in which light's electric field vibrates as the light travels. Ordinary light can contain many directions mixed together. Under certain conditions, however, light becomes slightly organized in orientation. The cosmic microwave background preserves such organization in a faint pattern spread across the sky. This pattern is far weaker and more delicate than the broad glow itself, yet it adds a finer layer of memory to the oldest directly observable light. If the temperature ripples show where the young universe is slightly warmer or cooler, polarization shows how the final interactions between light and matter are shaped at the threshold where that ancient radiation begins its free journey. The origin of this pattern lies in scattering. Before the universe becomes transparent, photons move through a sea of charged particles and are repeatedly deflected. As long as those scatterings continue everywhere in a dense way, the radiation field remains closely tied to the surrounding matter. Near the moment when the young universe thins enough for light to escape more freely, the conditions become just right for a subtle directional imprint to arise. A photon scattering from an electron can become polarized if the incoming radiation around that electron is not perfectly the same in all directions. The crucial ingredient is a slight directional unevenness in the local radiation field. If the arriving light is completely symmetric from every side, the preferred orientations cancel. If the radiation has a small quadrupole pattern, meaning that it differs across directions in a structured way, then the scattered light acquires a faint organized orientation. This sounds abstract, but the physical meaning is calm and concrete. At the last scattering surface, the universe is not perfectly smooth. Matter, motion, and radiation already contain small variations. These variations allow a tiny directional pattern to form in the light arriving at different electrons. When photons scatter one last time under those conditions, they leave behind a trace of that local geometry in their orientation. The result is polarization. It is not a separate light source and not a different background layered over the first one. It is part of the same ancient radiation, carrying additional information beyond temperature alone. Because the effect is so small, polarization remains invisible to ordinary human senses and difficult even for precise instruments to map. Yet once it is measured, it reveals a remarkable degree of detail about the state of the young universe. Orientation preserves something about motion, direction, and local structure at the time of release. This is why polarization is often described as a finer record. The broad glow tells that the universe is once hot and later cooled. The temperature ripples tell that the young cosmos is slightly uneven. The polarization pattern shows how some of those uneven conditions are written into the light through its last scatterings. Much of the observed pattern takes the form called E-mode polarization. The name is technical, but the concept can be stated simply. The orientations arrange themselves into patterns that can be described as radial or tangential around hot and cold regions on the sky. Radial means pointing inward or outward from a center. Tangential means circling around it. These arrangements arise naturally from density variations and velocity patterns in the ordinary matter and radiation of the early universe. Their presence is one of the strong confirmations that the basic picture of the early cosmos is sound. There is also another mathematically distinct kind of pattern, often called B-mode polarization. This pattern has a twisting character rather than the simpler radial or tangential one. Some of it can arise later when matter between Earth and the last scattering surface distorts the ancient light very slightly. On the largest scales, cosmologists also search for a deeper contribution that could come from primordial gravitational waves in the very early universe. That possibility remains uncertain. What matters most here is that polarization is not one undivided signal. It can take different geometric forms, and those forms help separate different physical causes. The polarization map of the sky therefore adds precision to the history already carried by the microwave background. It helps determine how ordinary matter moves in the young cosmos, how tightly radiation and matter remain linked before decoupling, and how local variations shape the last scattering process. It also improves measurements of other cosmological properties because the polarization signal can be compared with the temperature signal. When the two are studied together, the record becomes more complete. The same young universe is seen through brightness and through orientation. This is one of the quiet triumphs of modern observation. The oldest visible light is so faint, so cold, and so ancient that it might seem impossible for it to retain anything beyond a general glow. Yet the sky preserves more than that. It preserves texture in temperature and also order in orientation. The final touch of matter upon the ancient radiation is not erased by the billions of years of travel that follow. It remains measurable. There is a special calm in this kind of evidence. A star can be bright, a galaxy can be grand. Polarization is neither. It is subtle almost to the point of disappearance. Its significance comes not from obvious spectacle but from precision. The universe at the edge of direct sight does not only shine, it whispers in pattern. The light arriving now at detectors carries a preferred orientation impressed upon it when matter and radiation are just beginning to part company. That orientation survives the expansion of the universe and reaches the present as a delicate fossil of interaction. So the polarization of the cosmic microwave background stands as one of the most refined records within the oldest light that can be seen. It arises when photons scatter in a slightly uneven radiation field at the threshold of transparency. It preserves directional order left by the final encounters between light and charged matter. Much of it appears in the well-measured E-mode pattern, while other components remain harder to isolate and interpret. Together, these faint orientations add depth to the ancient glow. They show that the earliest visible light carries not only brightness and temperature, but also memory of how it is last touched. In this delicate ordering across the sky, the universe keeps one of its finest signatures from the moment it first becomes clear enough to see through. Before the ancient glow is released, before the universe becomes transparent, there exists an older reality that no ordinary light can show directly. It is not hidden because it is too far away in the simple sense. It is hidden because the medium of the young universe does not permit light to travel freely through it. This is the inward limit of cosmic sight. The universe has earlier phases than the microwave background, and those phases are older than the oldest light that can now be observed. But they do not remain visible in the same way, because the cosmos at that time is opaque. The barrier is physical, not merely technical. It does not arise because telescopes are still too weak. It arises because light from those earlier moments cannot pass through the hot, dense plasma without losing the direct path required for later observation. In this opaque era, matter and radiation remain tightly coupled. Free electrons fill space in great numbers. Protons and other nuclei are also present, and photons cannot cross the medium without repeated scattering. A photon moves only a short distance before being redirected. Then it is redirected again, and again. Under such conditions, there is no clean line of sight from one distant region to another. The universe is luminous in a deep internal sense, but its luminosity is trapped within constant interaction. To imagine it as a clear glowing landscape would be misleading. It is more like a dense radiative fluid in which light and matter continually influence one another. The very abundance of light prevents vision from reaching through it. This opacity extends backward through earlier and hotter ages. As time runs inward toward the beginning, temperature rises, density increases, and the physical simplicity of the universe becomes even more pronounced. Long before stars, long before atoms, long before the release of the microwave background. The cosmos consists of basic particles, radiation, and the rapid consequences of expansion in an extreme environment. Quarks and gluons, electrons, neutrinos, protons, neutrons, nuclei, and photons all belong to different early intervals of this inward path. The exact sequence is known in broad outline through well-tested physics, though some details remain uncertain at the highest energies and earliest instants. What matters most here is the principle. Older phases do exist. They are not imaginary spaces inserted to fill a gap. They are necessary chapters in the physical history of the universe. But they are not visible to later eyes through ordinary light because the universe is too opaque at those times for light to preserve an undisturbed message across the ages. Even the first light elements emerge in this hidden domain. In the first minutes after the Big Bang, protons and neutrons combine through nuclear processes to form much of the universe's helium and traces of other light nuclei. This stage, often called primordial nucleosynthesis, leaves a measurable legacy in the later abundances of the light elements. Those abundances can still be studied in the present universe, and they provide one of the strongest confirmations that this invisible early phase is real and well described in outline. Yet the process itself is not seen directly in surviving light. It is inferred from the matter left behind. In this way, the universe before sight begins is not unknowable, but it is known differently. It is reconstructed rather than watched. This distinction is important. There is a difference between what can be observed directly and what can be inferred with confidence. The oldest directly visible light comes from the later moment when the universe becomes transparent. The older opaque universe is not directly seen in that same electromagnetic sense, but it is not therefore beyond science. Its existence is supported by the structure of the microwave background, by the expansion of the universe, by the observed abundances of the light elements, by particle physics, and by the consistency of cosmological models across many measurements. The universe before direct sight is hidden, yet not arbitrary. It is veiled, yet not empty of evidence. There may also be other messengers from very early times that are not ordinary light. Neutrinos formed in the early universe should still exist as a relic background, though they are extraordinarily difficult to detect directly because they interact so weakly with matter. Primordial gravitational waves, if they exist at an observable level, could also carry information from very early phases, potentially earlier than the release of the microwave background. These possibilities matter because they show that the limit of sight is not necessarily the limit of all evidence. Still, as far as direct seeing through electromagnetic radiation is concerned, the barrier remains firm. The plasma of the early universe prevents photons from carrying a clear view from deeper times to the present. This is why the oldest thing that can be seen is not the oldest thing that exists. The universe is older than its oldest visible light. Earlier processes shape that light before it is released. Earlier conditions determine the matter content, the expansion history, and the first elemental composition from which later structures arise. But those older realities stand behind a curtain of opacity. The curtain is not darkness in the ordinary sense. It is too much interaction. The cosmos is too dense with charged particles, too full of scatterings, too tightly coupled for photons to stream freely across it. Only when expansion and cooling change the medium does light finally escape and begin the long journey that later makes vision possible. There is a calm finality in this limit. Astronomy can extend sight outward across billions of light years and backward across almost the whole history of the cosmos. It can detect faint galaxies from the first few 100 million years. It can map a microwave glow released when the universe is only a few 100,000 years old. It can measure temperature ripples and polarization patterns imprinted at the threshold of transparency. Yet, in the end, ordinary light stops there. The universe keeps older secrets behind a medium that no telescope can simply look through, because the barrier belongs not to distance alone, but to the physics of the early cosmic state. So the final inward region of this search is not a visible object, nor even a visible glow, but the domain before visibility begins. It is the older opaque universe, real and consequential, physically grounded and partly reconstructible, yet inaccessible to direct sight through light. It contains the earliest nuclear history, the hotter plasma state, and the deeper phases from which later transparency emerges. These are older than the oldest thing that can be seen, and precisely for that reason they mark the edge of the question. The search for the oldest visible thing ends at the boundary, where the universe first becomes clear. Beyond that boundary, the cosmos still exists, still evolves, and still leaves evidence, but it no longer offers itself to sight in the ordinary luminous way. Before sight begins, the universe remains present without being seen. The sky above Earth grows quiet again when the mind returns from these depths. Stars appear where they always do. Galaxies remain faint, scattered, and remote. Yet behind every visible point and beyond every dark interval lies a history far older than the eye first suspects. Some of that history can be seen directly in ancient light. Some of it can only be reconstructed from what that light later carries and from the matter left behind. The oldest visible thing in the universe is therefore not the oldest thing that exists, but the oldest light that still travels freely to the present. It comes from the moment the young cosmos first becomes transparent enough to remember itself in radiation. That answer is quiet rather than dramatic. It does not point to a lone object glittering at the edge of space. It points to a faint all-sky glow, older than stars, older than galaxies, and older than every luminous structure that later fills the heavens. Beyond it lies a still earlier universe, hot, opaque, and hidden from direct sight, where light exists but cannot yet escape as a clear messenger. The boundary between those states gives the visible cosmos its deepest horizon. In the end, the universe allows vision to reach very far, but not all the way. It offers a nearly complete visible memory and then closes the door with plasma and scattering. That limit is not a failure of observation. It is part of the structure of reality itself. The oldest light arrives, and older times remain veiled behind it. The night sky becomes, in this way, both revelation and restraint. It shows almost everything light can show, then stops at the first clear window. Beyond that window, the universe continues inward without image, leaving only traces, equations, and the calm knowledge that existence begins before sight.